mission of Air Force Systems Command is to develop and acquire new materials and systems in support of aerospace power. These systems must be of superior quality, yet affordable and maintainable, and above all, more than equal to the systems of a potential enemy. The GBU-15 cruciform wing weapon is a 2,000-pound class air-launched glide bomb that flies to the target using guidance updates. This weapon was developed by Air Force engineers by improving the early guided munitions used in Southeast Asia. Tactical air forces will use this weapon to destroy enemy defenses and other point targets. The cruciform wing weapon has precise accuracy from altitudes below 60 meters or 200 feet, and at standoff distances greater than 5 nautical miles or 9 kilometers. The weapon is equipped with a television guidance system. An imaging infrared guidance system for day, night, and limited adverse weather is under development. Based upon successful testing, studies, lessons learned in Southeast Asia and in the Middle East War, the Defense Suppression Program initiated full-scale development of the GBU-15 cruciform wing weapon. The following tests use inert warheads. Two basic methods of attack are available: direct and indirect. For direct trajectories, the weapon is locked on the target before launch and glides in a near line-of-sight flight to impact. The indirect method uses a mid-course glide phase that extends the standoff capability. Using this indirect method, the seeker can be locked onto the target after launching the weapon, or the pilot can fly the weapon manually to the target using guidance updates provided by the data link. The cruciform wing weapon's standoff and low-altitude launch capabilities definitely ensure increased survivability for tactical air forces. It will be part of the basic ordnance loads for attack aircraft involved in multi-mission operations. Russian ICBM technology has continued to improve since the 1960s. Their newer ICBMs, the SS-18 and the SS-19, have an imposing strategic capability. The Russians have approximately 1,400 ICBMs. The newer ICBMs are larger, more powerful, and more accurate than previous models. To counter this increased threat, the United States is developing the MX, which will enhance the survivability of our land-based ICBM force. The MX carries 10 warheads. Currently, the plan is to place a limited number of MX missiles in Minuteman silos. The MX sustains our strategic triad, and more importantly, it can set the climate for mutual strategic arms reduction talks. Current basing studies and later deployment will result in MX survivability into the 21st century. Is the codename for a phased array radar system installed on the aft deck of the United States naval ship Observation Island. Cobra Judy will collect data on foreign strategic missile tests. The Observation Island was originally a merchant ship built in 1953. It was overhauled and modified for the Cobra Judy mission. The Observation Island completed its initial sea trials and underwent system testing at the Naval Shipyard at Baltimore. The Cobra Judy antenna consists of thousands of small radar antenna elements, is 4 stories high, weighs 250 tons, and is installed on the aft deck of the vessel. The crew will be a combination of 64 Air Force people, contracted technicians, and 78 mariners who will operate and maintain the vessel. The Observation Island will operate in the Pacific Ocean from its home station at Pearl Harbor, Hawaii. The advanced aerial refueling boom has undergone various tests, as demonstrated on the new KC-10 tanker. A number of different aircraft have been involved as test receivers. The new electronic boom controls replace manual controls, thus giving the operator greater control. Here, a C-5 Galaxy cargo aircraft proves boom compatibility in its initial contact tests. This is the Universal Aerial Refueling Receptacle Slideway installation, which will become standard on most aircraft. The advanced aerial refueling boom also increases the separation distance between tankers and receivers. This makes the refueling faster and easier. For some time, the Air Force has been testing, evaluating, and improving the aerial refueling of its aircraft, thereby extending the various aircraft in performing their missions. The advanced aerial refueling boom has undergone tests for tracking, deployment, and stability, which involved retracting, automatic loading, and increased fuel flow. The boom is controlled through a fly-by-wire system that uses electronics in place of manual pressure. The boom operator has greater control, and the electronic system allows him to better use the boom's large maneuvering capability. The KC-10 will also have the probe and drogue refueling equipment for use with Navy and NATO aircraft. Other tests of the advanced aerial refueling boom on KC-135 tankers included different altitudes, airspeeds, fuel systems qualifications, and receiver compatibility tests on various aircraft. The advanced aerial refueling boom proved to be a significant improvement over previous booms. This is another example of Air Force planned improvement and modernization for the future. The Navstar Global Positioning System is a space-based network of satellites, transmitting precise, jam-resistant radio navigational signals. Current plans call for 18 satellites orbiting the Earth every 12 hours. They will provide highly accurate and continuous global coverage to authorized users by the late 1980s. The Global Positioning System can pinpoint an aircraft, land vehicle, or seagoing vessel within 16 meters or 52 feet of its actual location in longitude, latitude, altitude, and speed. The Manpack operator is demonstrating use of the 12-pound production Navstar GPS Manpack receiver. In this demonstration, the operator with the Manpack is hidden from the pilot's view. The operator has obtained his coordinates using the Navstar GPS and radioed them to the pilot. The coordinates were entered into the Navstar GPS receiver as a waypoint. Course to steer was presented on the helicopter steering display. The helicopter flew at low level to a point directly over the Manpack operator, without benefit of any visual markers in the pilot's view. This is a level bomb delivery pass at 5,000 feet with release of a dummy Mark 782 bomb. Target coordinates were entered into the Navstar GPS by the pilot. The system provided steering information and automatic release. Good accuracy has been achieved from both 5,000 and 10,000 feet. Very low altitude release will be available in the Phase 2 system. In addition to navigational information, Navstar applications are many and varied. When it is available, the Space Shuttle will be used to place Navstar satellites in orbit. To increase the B-52 bomber's capability to penetrate enemy defenses and destroy key ground targets, the Air Force is acquiring the air-launched cruise missile. Cruise missiles are pilotless aircraft powered in flight by a small jet engine. The 1,500 nautical mile range cruise missile begins operational deployment at Griffiths Air Force Base in New York. Initially, each aircraft will carry 12 missiles. That number may be increased to 20. Since cruise missiles attack prime targets at substantial distances from the carrier aircraft, the B-52 cruise missile combination can saturate enemy defenses and complicate his ability to defend his territory. Cruise missiles fly intricate routes to their selected targets using the terrain contour matching guidance system called TERCOM. The TERCOM system examines surface contours during flight and compares them with computerized contour maps of the flight route stored in the missile's guidance system to determine its location. Through the use of frequent position updates from its TERCOM system, the missile is able to achieve pinpoint accuracy. Launched from the B-52s in large numbers, cruise missiles at very low altitude practically defy detection. The Air Force has the option of modifying additional B-52s to carry the cruise missile. This option becomes available in 1986. The EF-111A is the first Air Force tactical jamming system platform specifically designed for operation in a multiple electronic countermeasures environment, such as the East European theater. The mission of the EF-111A is to suppress and jam all long-range, early warning, ground control intercept, height finder, and acquisition radars. The EF-111A can stand off or penetrate, along with or ahead of a tactical strike force, jamming radars of an enemy defense network. With its electronic warfare jamming system, the aircraft provides our strike forces with three-way protection, as an escort into and out of target areas, as a jammer on close air support missions, and in a loiter mode to protect our aircraft over hostile territory. It is also capable of protecting itself against terminal threat radars. When known threats are identified, appropriate countermeasures can be initiated automatically or manually at the operator's discretion. The system can discriminate against radar signals by frequency band, specific frequency, pulse width, or direction of arrival. A built-in test feature allows the electronic warfare officer to perform a confidence check of the system and isolate malfunctioning components. This test feature is also used by ground personnel as a method of pinpointing malfunctions during pre-flight or regular maintenance checks. The EF-111A tactical jamming system, operating alone or in groups, will provide the tactical commander in the field with many more options in defense suppressions. It will play a key role as a force employed against the electromagnetic threat in support of ground-air operations. The EF-111A is effective against a simulated East European netted radar environment, which includes manned acquisition and early warning radars, and a generated electronic environment of multiple radars and hundreds of signals. At the Utah Test and Training Range, the Air Force conducted a flight test of the BGM-109 Tomahawk Ground-Launched Cruise Missile, or GLICM. GLICMs are launched from transporters, capable of off-road movement and quick deployment to remote locations. 4 transporter erector launchers, each with 4 missiles, and 2 launch control centers will constitute an Air Force tactical GLICM unit. The missile is propelled from the launch tube by a solid fuel boost motor. Seconds after launch, the boost engine is jettisoned. The wings, tail fins, and engine intake extend, and the turbofan engine starts. The 1,500-mile range Glickem is equipped with a highly advanced terrain contour matching guidance system, which compares a radar picture of the flight path with previously stored data to guide it to the target. All primary test objectives, including launch from a transporter erector launcher, transition from boost to cruise flight, separation of the boost engine, and sustained cruise flight, were met. Glickem procurement started in fiscal year 1981, and initial operational capability is scheduled for December 1983. Is a fixed-based, solid-state, phased-array radar warning system for detection and identification of sea-launched ballistic missiles. The radar system is contained in this 105-foot-high building. 5 floors house radar equipment, maintenance areas, office space, and a cafeteria. Each system consists of a dual-faced phased-array radar with data processing and control hardware. The radar has a very high probability of detecting targets of 10 square meters at a maximum range of 3,000 nautical miles. Each face operates over an angle of 120 degrees. Thus, the sight scans a total of 240 degrees. The system is highly automated, and thus the operator needs few controls over radar performance and message generation. The system now consists of 2 sites, one at Otis Air Force Base, Massachusetts in the east, and at Beale Air Force Base, California in the west. Current plans are to establish 2 more sites, Warner Robins Air Force Base, Georgia, and Goodfellow Air Force Base, Texas. The data obtained is supplied to NORAD Cheyenne Mountain Complex, Strategic Air Command, the National Military Command Center, and the alternate National Military Command Center. The AGM-65 Maverick is the Air Force's versatile, rocket-propelled air-to-surface missile. The laser-guided AGM-65C was replaced by the laser-guided AGM-65E, built for the Marine Corps by the Air Force. Up to 6 Mavericks can be loaded on a fighter aircraft. Thus, several different targets can be attacked on a single mission. The Maverick was designed for launch by tactical aircraft against targets such as bunkers, parked aircraft, armored personnel carriers, tanks, radar or missile sites, and field fortifications. The Laser Maverick is being developed primarily for close support of combat troops. Here it is tested against a ship target. An airborne or ground-based laser designator illuminates the target with a spot of laser light invisible to the naked eye. The Maverick's seeker scans for the spot. The Laser Maverick, operating day or night, upon detecting the coded signal, automatically locks on and tracks the designated target. Because of laser designation, the Maverick can be fired safely at targets near friendly troops. The attacking aircraft can launch the missile and leave the area without visually identifying the target, and thereby increasing the survivability of the flight crew. The AGM-65E missile is to be equipped with the heavier 300-pound blast penetration warhead. Selectable fuses give flight crew the choice of having the warhead detonate on impact or for greater effects after penetrating the target. A high degree of interchangeability is maintained between the various Mavericks. Cockpit-related functions, launchers, and test equipment are the same or very similar. The Defense Communications Agency is continuing the development of a worldwide strategic communications system called the Defense Satellite Communications System, or DSCS. The Air Force is responsible for the program from development of the satellites to final orbiting and checkout. When the satellite is operational, it's turned over to the Defense Communications Agency. The Defense Satellite Communications System consists of 4 active satellites, 1 over the eastern Atlantic and 1 over the western Pacific. A 3rd satellite is located over the eastern Pacific, and there is a 4th over the Indian Ocean. Up to 2 spare satellites are available on orbit to provide rapid replacement of failed satellites. The satellites, each with a 10,000-mile diameter view, cover the Earth, except for certain polar areas. The communications satellites are in synchronous orbits. Thus, from the ground, they appear to be stationary, turning as the Earth turns. The communication equipment handles 1,300 voice channels, with a secure command capability for the satellite command and control signals. Information is received and transmitted by any combination of the 4 antennas. The narrow beam antennas each cover an area about 1,000 miles in diameter. They can be pointed at desired locations by ground command. The 2 wide beam antennas each cover an area more than 10,000 miles in diameter, or the side of the Earth facing the satellite. Power for the satellite is supplied by solar cells. 3 nickel-cadmium batteries supply power during eclipses, when the sun's rays are blocked from the solar cells. Ground commands fire jets on the satellite to maintain its altitude and position in orbit. 2 new advanced development satellites, Discus 3s, are slated to be launched in 1982 and 1983. They will be used to test the new satellite design. Future Discus 3 satellites will be delivered in orbit by the Space Shuttle. Program development continues with new, higher-capacity Discus 3s designed to fulfill communications needs and to meet unexpected jamming conditions in the 1980s. The Defense Satellite Communications System provides a complete global communications network, serving our nation's defense need. Of October 1981, President Reagan announced a plan to develop a variant of the B-1 bomber. The plan is to build 100 B-1Bs with the expectation of having the first B-1B squadron operational in 1986. The B-1B will be built to replace the aging B-52 bomber. The B-1B program will permit more time for the planned advanced technology or stealth bomber to be fully developed, both technically and operationally. The B-1B will incorporate the latest proven technical advances and will provide payload versatility. For example, an additional 14 cruise missiles can be carried along the fuselage externally. Recently completed studies, plus the bomber penetration evaluation flight tests, show the B-1B capable of penetrating advanced Soviet defenses and can maintain that capability into the 1990s. While the cruise missile is extremely accurate, they are only effective against targets of fixed location and known value prior to launch. The B-1B, manned by an experienced crew, can place at risk potential targets whose location or status are uncertain when a conflict begins, but are presently safe from our arsenal of retaliatory weapons. The B-1B long-range combat aircraft is the product of over 19 years of studies and evaluation. The crew consists of pilot, co-pilot, offensive systems operator, and defensive systems operator. Its weapon bays allow carrying of nuclear air-to-surface missiles, nuclear or conventional gravity bombs, and other weapons or fuel depending on the mission requirements. 2/3 the size of a B-52, the B-1B can carry a payload almost twice that of the B-52, and the B-1B has a cross-section significantly lower than the B-52. Its swing wing permits it to get airborne faster and use less runway than a B-52. Thus, more existing runways will be available for use. More airfields with shorter runways allow greater dispersion, and reduce potential aircraft losses. The B-1B will incorporate all the latest electronic systems and will use ejection seats rather than the crew ejection capsule. 4 General Electric turbofan engines will power the B-1B at high subsonic speeds at treetop altitude with an unrefueled intercontinental range. The B-1B also has a higher penetration speed and a lower penetration altitude than the B-52. 2 of the initial B-1s will be used in testing selected systems and operations that may be incorporated into the production of future B-1Bs. On April 12, 1981, the first manned and reusable spacecraft, Columbia, lifted off Pad 39 at Kennedy Space Center, with astronauts John W. Young and Robert L. Crippen at the controls. The 36-orbit 54-hour flight success was due in part to support provided by Air Force Systems Command Space Division and its detachments around the world in this joint NASA-Air Force program. The key objective of the flight was testing and evaluating the various shuttle systems. A highly critical objective was satisfied when astronaut Crippen successfully tested the opening and closing of the space shuttle's cargo bay doors. This was important because of the need to expose the large radiators on the inside of the doors that dissipate heat from the onboard systems. In the future, space shuttles will be launched and recovered from equatorial orbits at Kennedy Space Center. Polar orbits will be flown from Vandenberg Air Force Base. Edwards Air Force Base will continue to be a backup recovery base for both types of orbital flights. The perfect landing at Edwards Air Force Base on April 14th concluded the first manned space tests, with 3 more orbital flight tests to go. The Space Shuttle and the other systems you have seen are a few of the highlights of Air Force Systems Command research, development, test, evaluation, contracting, and manufacture. Only by vigorous and progressive programs can we maintain the edge in aerospace power.